Hello, everyone. We're going to go ahead and get started here. In this next talk, we have Fabiana Clemente, who will be giving us a 30-minute presentation on the importance of synthetic data and data-centric AI. And so just like the last session, we'll have 30 minutes for the speaker, and then 5 minutes or so for questions.
Awesome, awesome. So what does it mean, the importance of synthetic data in data-centric AI? Data quality, in a nutshell. So why data quality is so important? That's what we're going to talk about and why synthetic data can play a role in it. So I'm Fabiana Clemente. I'm Chief Data Officer at ydata. My background is in applied maths. I work for big enterprises and startups. I did from data science to data architectures. And I do love, and my interests are in data science, for sure, time series, and generative models. So we are in this era of foundational models. We talk a lot about them and how they are changing the AI and our landscape in terms of data science. But the truth is, this type of models need lots and lots of data. So they are very data savvy. And you might have not seen that, but we all are aware of ChatGPT, and we know how much data it consumes and needs. But in one of the latest articles about it, it was shown that with far less data, but more accurate data, we can train a model as good as the one that we are seeing being used in ChatGPT. That's awesome, right? So this already tells you a lot about the importance of data quality. It's not only about how it makes your model more accurate and better, but also more cost efficient, and you can train it way faster. That's impressive. So we need to think about data as a product. And it means that we need to define really well the business needs at the heart of our data flows and preparation for a better design and to answer better the needs of a business. You might be wondering how this all ties up with synthetic data. I'll reach to that part. So, what is synthetic data? I know you have the definition here, but in case someone wants to go ahead and tell your own perception of what is synthetic data, please go ahead. Oh, you probably are still a bit shy at the moment, so I'll take that as a not for now. So synthetic data is artificial generated data that was not collected from real-world events. It keeps the same characteristics as the real data, and it's not traceable back to the original individuals. Sounds easy. So how can we generate synthetic data, or what types of synthetic data can we consider? Yes, not all synthetic data records are the same. There are different layers and different aspects to and different needs for the synthetic data generation. The one that you probably are aware of, and you might have already used it at any time of any moment while you are developing, is dummy data. You probably know, for example, packages like Faker. They do deliver you exactly this, dummy data. It's useful data for some use cases, for example, stress testing systems, but it's data that probably you won't be using for development of machine learning. Data-driven synthetic data. This is the one I'm going to focus more on this talk, and this is data that we have generated synthetically based on a model that was able to learn the structure and behavior of the original data. This synthetic data that is generated is feasible to be used for machine learning purposes because it holds the same value and the same behavior of the original data, while still being synthetic. And last but not the least, simulated data. This is probably one that you have heard about, especially when we have agent-based simulation. But we are observing more and more need for this type of data. For example, for risk modeling in financial services, this is a very useful type of synthetic data. And this means that in a simulated scenario, the synthetic data picks up the characteristics of the real world data, and it enables extrapolation of scenarios based on past events. Another example is when we see an image from a car, and we want to see that same image of that car in a snow kind of environment. That's simulation, and that's still useful. It depends on the business needs. So, okay, one of the most common questions that I get while talking about synthetic data is why then go synthetic? I think the last slide was already convincing enough, but if you have real data, does not mean your real data is enough for what you want to build. And synthetic data can allow you to become cost and speed, or give you less cost and more speed in terms of data acquisition, can help you to unlock data sharing and access to data in a more timely manner. It supports responsible AI by allowing to debiasing your data sets. It helps in enhancing the machine learning performance. And last but not the least, it can be an enabler to product testing and development. Now, and I promised that I would focus more on synthetic data driven, and that's exactly what you can see in this diagram. I've shown you in the beginning of the presentation that one of my passions are generative models. And in this case, you can see a tree of the different deep generative models that you can follow for the generation of synthetic data. All of them will enable you to generate synthetic data, but all of them have different needs, different requirements, and have different performances in what concerns the generation of data. We have implicit density, explicit density. I know some of you might have heard Markov chains. Yes, they are generative models, although they are in the whole books of statistics. But you also have models such as generative matching moment nets. You have generative adversarial networks. You can use as well variational autoencoders for the generation of synthetic data. And in more detail, you can use as well Bayesian networks, for example. I'm going to show you this just to showcase the difference of the benefits between different models and different use cases. For example, Bayesian networks are suitable for smaller and more noisy data sets. They are great to handle the complexity and dimensionality of data from verticals such as healthcare, for example. And they are able to. The problem is that the order of the columns of your data do have an impact on how these models, for example, behave, which make them hard to have success with no prior knowledge. They are hard to scale for larger volumes of data as well. So if you have a small, noisy data set in a vertical where you have high dimensionality, for sure Bayesian networks are more than enough for you. But if you are in a vertical where your data sets are very big, Bayesian networks will be a pain for you. Nevertheless, they also have one thing that is very good, and they are very explainable. So when you generate synthetic data using Bayesian networks, you kind of get an understanding of how your data behave and how it looks like. Transformers. They are also very good for the generation of synthetic data. And in this case, text, NLP, image, structured data, time series, they are pretty flexible in terms of the data types they can generate. They do not suffer from mode collapse, which is great. They easily scale with the volume of data and can be easily adapted to different data types. Nevertheless, they are data savvy, so they are not suitable to synthesize smaller data sets. For example, healthcare. Probably it's a place where you don't use transformers. They won't be able to generate data unless you have pre-trained models and you use, for example, things like transfer learning. Then you might be able to enable transformer architecture, for example. They are also hard to explain. And they are very hard to control in terms of business constraints. And why is this relevant? Verticals like financial services, they require the explainability of any machine learning model that you use. So if you are using synthetic data inside of verticals such as financial care or even healthcare, you probably don't want to go with this type of architecture. And last but not the least, generative adversarial nets. They are super fun. Their concept is really great. If you go and check, it's a competition between two different networks and in a min-max game. So it's an optimization kind of problem combined with competition. The way they were created is pretty fantastic, and they are very flexible to different use cases. It's not only synthetic data they allow, they have different applications. So this type of architecture does easily scale with the volume of data and can be easily adapted as well for different types of data. So NLP, structured data, time series, images, we have seen different architectures, and they are very, very flexible. They do have a huge benefit, which is the introduction of variability to the generated synthetic data, which is great for privacy-compliant use cases. They are hard to optimize and fine-tune, and they can suffer from mode collapse. There are many papers about the mode collapse in generative adversarial nets, and there are just few about also their optimizations. For example, using the traditional methods for optimization like stochastic gradients is not great for them. It's almost impossible for you to optimize this type of network with those. You probably want to go with evolutionary kind of approaches with genetic algorithms, for example. And, okay, this was about how can I generate it. Another question that I commonly get about synthetic data is how good is my synthetic data, and how can I trust the synthetic data that was generated? I have to disclose that this is a tabular data edition. If you want to go for images, time series, there are nuances that you should follow when validating your synthetic data. Nevertheless, all the data types probably have these three pillars or dimensions where you want to validate your synthetic data. Fidelity, which stands for how similar is the synthetic data compared to your original training data. So is it representative of the data that you have learned from? Is it useful? So can it be used for in replacement of real data for downstream applications? And downstream applications can be, of course, machine learning models, forecasting systems, but it can also be an analytics system, for example, just a dashboard or the construction of a pipeline or a data engineering pipeline where you want to do tests. And last but not the least, privacy. So do we have in the synthetic data any leakage from the real data that we have learned from? And this is probably the important part of the definition of privacy here. We are validating if we are leaking from the data that we have learned from, not validating that the synthetic data, when released in the real world, does not leak any privacy regarding everything. So this is different because that's the concept overall of GDPR, which is if any data set is combined with any source of data, internal or external, it must not have any re-identification. In this case, the definition of privacy is regarding re-identification between the original and the synthetic alone. So this is one of my favorite sentences of all times. This was said by Manuela Veloso from JP Morgan and Chase. The realism of data is overrated. And this is true. It's true, and you have, for example, a very good use case, which I do think it was Uber who built it out with GTNs, where they have shown that they were able to generate synthetic images that for a human being, they did not make any sense. We were not able to see cars, people, streets, nothing. It was just gibberish. And for the models, It was one of the best data that the models could use to identify the type of patterns they wanted. So that's really a proof that the realism of data in real-world data is super overrated. And keeping how you can build a system to validate your synthetic data set, you should start by ensuring you are not overfitting. Let's not forget that, especially for synthetic data-driven, you are still using machine learning, or you are still using models for the generation of that synthetic data. So make sure you do not forget to use the same principles you usually do when you are building your machine learning model. Create an holdout. Create a set of data that is unseen by your synthetic data generator. That will allow you and ensure you that the synthetic data that is being generated is, in reality, generalizing well. You can do different types of holdout. You can do the train test split. You can do cross-validation. It depends on your use case. But be sure to implement this. Second, you might want to go for a profiling of your data, or exploratory data analysis, or where you just extract some metrics, means, maximums, divergency scores, check if the distributions are similar, check if there is missingness and you are replicating the same missingness as on your original data. This all should be validated. For example, are you generating the same category coverage? How are the outliers behaving on your synthetic data generation? That's what you should account for. In this case, I'm just plotting here an image from our open source, the ydata profiling. It gives you the full profile of a data set. In this case, I've used it also to validate synthetic data. So here are some of the metrics that I was explaining: univariate, category coverage, numerical range, statistical similarity, FID score if you are using images, for example, divergences like KL divergence. In a bivariate and multivariate, you might want to go with pairwise distributions, mutual information, and correlation matrices. If you are using with tabular data, don't forget in your correlations to always ensure that you are validating categorical to categorical, numerical to categorical, and numerical to numerical relations. Don't just use Pearson straight off, okay? Utility, downstream applications. It will depend, but these two are probably my preferred ones. Unsupervised, if I want to validate whether my analytic systems or reporting system will behave as expected, we do prepare a bunch of queries that we would do to the original data, do the same queries to the synthetic data, and check if the answers match or have a match within a certain tolerance. You also have the supervised version, which is assuming you know you have a target and you want to build a machine learning model. You go and implement a flow of test synthetic, test train, sorry. Yeah, I have a typo there. So, no, train synthetic, test real. Sorry for this. Where you do train your machine learning model on the synthetic data and you validate it on the real one. What does this do? You already have your baseline, right? You are able to train your model on your real data. So you know the performance of your real data. If you train a model on the synthetic data and you compare the results of the test set with of the real data, you can get whether your synthetic data is losing information. And that's how you do it. So you compare the results of your synthetic data against the test set of the real one. This is one of the best ways to ensure that you haven't lost information. Of course, you had all that validations around fidelity, but there's nothing better and more informative than a TSTR. And last but not the least, about privacy. We have the nearest neighbors, or KNN, which validates whether around your synthetic data, how many real records do you have. This allows you to go to several dimensions of comparison and allows you to understand, for example, whether a synthetic point was generated out of a single real record. That's a true risk of leakage, for example, because you can very easily re-identify what was the record that, for example, was the origin for a certain synthetic event. The second one is more complex, more interesting, and also more complete in terms of the validation of privacy, which goes for membership inference attacks. So what does this mean? This means that in a scenario where we provide synthetic data to someone, that someone is able to train a model on top of the synthetic data, and afterwards attack your real data in order to, attack the synthetic data in order to re-identify something from your original data. So based on only having access to your synthetic data, can a person, by building a model, attack your real data and know some specifics of the behavior? For example, things that are very dangerous to re-identify or to be able to reconstruct are what we call quasi-identifiers, like age, gender, postal code, all of that, even when redacted, can be re-identified, and the access to synthetic data can be a potential source of more information so you can reconstruct something on real data. That's what membership inferences attack measures in the end. There are more privacy metrics, of course, but these are the two more robust that are known in terms of literature. And this, again, is only valid for tabular data. This is not valid for example data sets where you have temporal dependency or you have relation in between records. For the membership inference attack, it's true, but not for example KNN. You cannot apply KNN for time series when you are validating the privacy of your generated data. So, to wrap it up, I have here some examples of synthetic data in the industry. We have JP Morgan that is using synthetic data to replace real data for analytics purposes, for example. So they have a problem of access to data. There are many privacy regulations that are blocking the use of the real data for development, for example. So they are using synthetic data for that purpose. Alexa, which is in a lot of ways trained with synthetic text data. And last but not the least, on the healthcare side, we have Carité Lab using synthetic data for privacy compliance. What does this mean? They need to have access to hospital data and other healthcare institutions in order to develop their solutions and their research. So they are using synthetic data exactly for their purpose. So they can keep evolving their investigation and their research in that sense. So just to wrap it up, synthetic data comes in many forms. It is able to capture the complexity of many data sets, can be used to address data quality issues, such as missing data, biases, augmentation. Synthetic data is a cost-efficient and can remove access barriers. And it's an emergent tech that, of course, still have some limitations, but that has a huge potential. I hope you have enjoyed the talk. Of course, if you want to geek out, we have a lot of open source about it. It's MIT licensed, so you can really explore it. You have here the QR codes in case you want to give it a go afterwards. We have, for example, I have here that I can show you, a Google Colab that you can very quickly spin in order to use, for example, one of the most known GANs for tabular data, which is CTGAN. This is a TensorFlow implementation. You can use it right away just to test out how your synthetic data will look like. And that's it. Let me know if you have questions. Hope you have enjoyed. Thank you.